February 26, 1943. Near Sidi Bou Zid, Tunisia. A battlefield, scattered with burnt-out armor, stretched beneath the desert sun. Recovery teams from the 10th Panzer Division approached a single American M4A1 Sherman tank, standing largely intact among the wreckage. German engineers inspected it carefully. The hull showed bullet scars but no penetrations. The tracks were functional. The drivetrain appeared undamaged. This was an intelligence prize. Under Heereswaffenamt order, the tank was marked for immediate shipment to Kummersdorf proving ground near Berlin. German doctrine valued precision mechanics, sophisticated engineering, powerful guns. American tanks, they believed, sacrificed quality for quantity. This Sherman would confirm those assumptions. When the test results arrived months later, they revealed something German engineers had never encountered. The Americans had built reliability that German industry, for all its precision, could not replicate. March 1, 1943. Gabes Railhead, Tunisia. A technical officer from the 10th Panzer Division signed the transfer manifest as the captured Sherman was craned onto a flat car under armed guard. The paperwork listed it as captured enemy vehicle. Recovery notes emphasized the condition: intact drivetrain, complete tool stowage, standardized fittings throughout. No improvised repairs or field modifications visible. Frontline reports described American armor with dismissive confidence. The Sherman stood tall, making it an easy target. Its 75mm gun lacked the penetrating power of German weapons. Intelligence briefings labeled American tanks as adequate but unimpressive. Yet those same reports contained contradictions that troubled careful analysts. American armored divisions maintained operational readiness rates exceeding 85%. German panzer units averaged 60% on good days, often falling below 50% during sustained operations. The shipping orders directed the vehicle to Kummersdorf for detailed technical evaluation, then to Hillersleben proving ground for endurance trials. Prüf 6, the German Army's weapons testing directorate, would conduct the analysis, standard procedure for captured equipment, identify weaknesses, assess capabilities, confirm German technical superiority. The manifest listed extensive spare parts stowed in the tank: track blocks, engine filters, transmission components, full sets of tools for field repairs. The quantity seemed excessive by German standards, where mechanics made do with minimal equipment and improvised solutions. American doctrine apparently expected frequent maintenance performed by ordinary soldiers rather than specialists. This suggested inferior construction requiring constant attention and adjustment. The flat car joined a convoy heading north through Tunisia toward the Mediterranean coast. The tank would travel by ship to occupied France, then by rail to Brandenburg. The journey would take weeks. Meanwhile, German engineers at Kummersdorf prepared for its arrival, anticipating confirmation of American industrial crudeness. April 5, 1943. Kummersdorf proving ground, Brandenburg. The Sherman rolled into a measurement bay. Engineers surrounded it with calipers, hardness testers, micrometers, precision gauges. The methodical work of technical assessment began according to established protocols. The team expected crude American manufacturing. Mass production necessarily sacrificed precision for speed, according to German engineering philosophy. Components would show loose tolerances. Assembly would reveal shortcuts and expedient solutions. Materials would be adequate but unremarkable. German tanks represented craftsmanship, the product of skilled workers and engineering excellence. American tanks represented industrial expedience, quantity over quality. The teardown began with the transmission, the heart of any tracked vehicle's mobility. German engineers removed the 5-speed synchronized unit and placed it on an inspection bench. The gearbox used helical gears, specifically herringbone-cut teeth, that distributed loads evenly and reduced noise. The design principle was unremarkable, well understood in German engineering circles. The execution was extraordinary. Measurements revealed tolerances as tight as anything produced in German factories. Gear teeth showed uniform hardness across all surfaces, indicating consistent heat treatment. The heat treatment itself was uniform throughout each component, not just surface hardening. Surface finishes were remarkably smooth. The housing castings contained no visible flaws or inclusions. Every part appeared precisely interchangeable with identical parts from other vehicles. The inspection team documented oil passages, bearing surfaces, shaft alignments with growing professional interest. Workshop sheets noted surprisingly low gear tooth wear, despite the tank having seen combat operations in North Africa. Internal comments recorded observations that contradicted fundamental expectations. The transmission showed what engineers termed industrialized precision, components manufactured to exact specifications through mass production processes that somehow maintained quality levels associated with careful hand craftsmanship. The steering system used hydraulically assisted controls that reduced driver effort. The clutch was modular, designed for rapid replacement rather than repair. Air filtration was multistage, protecting the engine from desert sand and extending component life. Access panels allowed mechanics to reach critical components easily, without extensive disassembly. Everything suggested design intent, focused on field maintenance by soldiers with basic mechanical training, rather than factory specialists. German tanks required specialists for major repairs. Transmissions were complex assemblies that demanded expert adjustment and calibration. The American system appeared designed for ordinary mechanics using standard tools and straightforward procedures that could be taught quickly. The engineering team leader made an unusual request. He wanted authorization for endurance trials. This was uncommon for captured equipment. Typically, static inspection sufficed to understand enemy capabilities. Vehicles were photographed, measured, weighed, documented, then destroyed or relegated to training demonstrations. But the preliminary data suggested something unexpected and professionally intriguing. Component wear rates appeared remarkably low. If maintained properly, using the procedures indicated in captured technical manuals, this transmission might outlast German equivalents by significant margins. This possibility demanded verification through actual testing. May 10, 1943. Reich Ministry of Armaments and War Production, Berlin. A summary folder reached a senior desk bearing Albert Speer's name. Enemy Tank Analysis, SHE, American M4 Sherman. The report sat alongside monthly production tables showing German armored vehicle output and resource allocation. Albert Speer, appointed Minister of Armaments and War Production in February 1942 following Fritz Tott's death, had driven German production increases through rationalization and centralization of authority. German tank output had risen from roughly 4,000 units in 1941 to projected figures approaching 12,000 for 1943. This represented substantial achievement given Allied bombing campaigns and resource constraints that grew worse monthly. The folder contained preliminary findings from Kummersdorf, technical details about American transmission design, component quality assessments that contradicted expectations, observations about field maintenance provisions that suggested different engineering philosophy. The data painted an uncomfortable picture for those who believed German engineering superiority was self-evident. Speer compared American production figures available through various intelligence channels. In 1942, the United States had manufactured 24,997 tanks, according to multiple independent sources. German production that year totaled approximately 4,200 units. The Americans built nearly 6 tanks for every one Germany produced. Intelligence analysts debated whether these figures included every armored vehicle type, potentially inflating the comparison. But even conservative estimates that excluded tank destroyers and specialized vehicles showed massive American production advantages that couldn't be dismissed as propaganda. The report included detailed analysis of American spare parts provisioning documented through captured supply manifests and prisoner interrogations. Each American armored division carried extensive replacement components distributed through unit supply chains. Engines could be swapped in hours using standard hoisting equipment and prescribed procedures. Transmissions were modular units replaced rather than repaired in forward areas. Track blocks were standardized across vehicle types, allowing inventory consolidation. Filters, gaskets, bearings, electrical components, IBI, all stocked in quantities German units never received even during initial issue. Training documentation captured with the Sherman revealed another significant difference in approach. American tank mechanics received instruction using automotive industry methods adapted for military equipment. They learned specific repair procedures for common failures through repetition and hands-on practice. They practiced component replacement on training vehicles until procedures became routine. They qualified through standardized testing that verified competence in prescribed tasks. The system assumed mechanics would be ordinary soldiers with basic mechanical aptitude, not specialist technicians with years of training. German doctrine favored quality over quantity, building fewer vehicles to higher standards with more powerful weapons and thicker armor. But this philosophy assumed German technological superiority would provide battlefield advantages that compensated for numerical disadvantages. The Kummersdorf data suggested American automotive engineering might have achieved both quality and quantity through different approaches that emphasized simplicity, standardization, and maintainability rather than sophisticated complexity. Marginalia on the report noted the difficulty of standardizing production under current wartime constraints. Allied bombing disrupted manufacturing continuity. Skilled workers were conscripted into military service. Materials became increasingly scarce, forcing design compromises. Design changes incorporated improvements, but prevented long production runs with stable tooling and refined processes. Each of these factors degraded German industrial capacity incrementally, creating cumulative effects that couldn't be easily reversed. Authorization was granted for comparative running trials at Hillersleben Proving Ground. The Sherman would be tested alongside representative German types, Panther Ausf, D, Tiger I, Panzer IV, to directly compare reliability and maintenance requirements under controlled conditions that would generate objective data. June 12, 1943. Hillersleben Proving Ground. 4 tanks lined up on the test circuit. M4A1 Sherman, Panther Ausf, D from recent production. Tiger I, representing German heavy armor. Panzer IV Ausf, G as the standard medium tank. Test crews received fuel allotments, oil supplies, route sheets, specifying the testing protocol. The trial protocol was straightforward and scientifically rigorous. Each tank would run continuous circuits covering approximately 100 kilometers daily. Crews would log all mechanical issues without exception. Maintenance personnel would perform only authorized repairs using standard tools and procedures specified in technical manuals. No specialist intervention allowed, except for catastrophic failures. The test would continue until major component failures required workshop-level repair that exceeded field capabilities. German confidence in the Panther was substantial and perhaps over-optimistic. The newest German medium tank mounted a powerful 75mm high-velocity gun with excellent armor protection using sloped design principles. It represented the future of German armored warfare, incorporating lessons from combat against Soviet T-34 tanks. Recent production vehicles incorporated improvements addressing early model deficiencies. The transmission was a new design specifically engineered to handle the vehicle's 45-ton weight. On the first day, all 4 tanks completed the circuit without serious issues. The Sherman felt heavy to its German driver, but responded predictably. Controls were well placed and logical. Visibility was good compared to German designs. The engine pulled steadily, despite the vehicle's substantial weight. Day 2 brought the first problem that would prove prophetic. The Panther developed transmission difficulties during the afternoon circuit. Gear changes became difficult, requiring excessive force. Strange noises emerged from the gearbox housing that experienced mechanics recognized as bearing distress. The crew reported increasing resistance on the shift lever that suggested imminent failure. By evening, the Panther was withdrawn for inspection before catastrophic damage occurred. The transmission showed premature wear on several gears that should have lasted thousands of kilometers. The final drive exhibited stress fractures in components that should have been robust. Oil contamination suggested seal failures, allowing debris into the lubrication system. The vehicle had covered less than 400 kilometers, far below acceptable service life expectations. Workshop personnel replaced the transmission assembly entirely, requiring specialized tools and 3 days of work by experienced technicians. The Sherman continued operating without complaint. Gearbox oil sampling showed normal wear particles within acceptable parameters. Brake and steering evaluations revealed no degradation. Track tension remained stable without adjustment. At 1,000 kilometers, maintenance crews performed scheduled service according to captured American technical manuals. Oil change using standard procedures. Filter replacement with parts from the vehicle's own stowage. Basic inspection of accessible components following checklist procedures. The work took 4 hours, with standard tools available to any unit mechanic. The Panther failed again at 800 kilometers after its transmission replacement. Different failure mode this time, but equally serious. The final drive overheated under sustained operation, indicating inadequate cooling design. Bearings were damaged beyond field repair limits. Again, workshop repair was required using specialized equipment and expertise. The Tiger I experienced final drive distress at 600 kilometers. The massive vehicle's weight, exceeding 55 tons, stressed components designed with inadequate safety margins for sustained operation. Repairs required specialist attention and replacement parts that would take days to obtain through supply channels, assuming parts were available at all. By kilometer 2,300, the Sherman had not required major component replacement, minor maintenance only, all performed according to schedule. Scheduled service, as specified in American manuals, using procedures any trained mechanic could execute. The gearbox oil showed remarkably clean condition, indicating minimal internal wear. Wear measurements fell well within acceptable ranges, with projected service life extending well beyond test duration. The test logs documented something German engineers found difficult to accept professionally. The American transmission demonstrated what the report termed überlegene Dauerfestigkeit, superior endurance, derived from what engineers identified as automobile industry methods. A draft conclusion stated with unusual directness, enemy vehicle exhibits reliability characteristics substantially exceeding German standards for equivalent components. Construction methodology prioritizes field maintainability and component longevity through design choices adapted from civilian automotive mass production. Precision manufacturing of individual parts creates assemblies requiring minimal adjustment during service life. Maintenance procedures are simplified to permit execution by personnel with basic mechanical training rather than specialist expertise. The implications troubled German engineers, who understood what this meant for sustained operations. German tanks achieved technical sophistication through engineering excellence and careful craftsmanship. But if that sophistication created maintenance vulnerabilities and reduced operational availability, then tactical superiority became strategically irrelevant when vehicles couldn't maintain readiness to fight. July 5, 1943. Kursk Salient, Soviet Union. Army Group South staff officers collated daily readiness returns as Operation Citadel, Germany's summer offensive, began with high expectations. The reports painted a concerning picture within the first 48 hours that contradicted optimistic planning assumptions. Panther battalions reported significant mechanical casualties that had nothing to do with enemy action. Of 184 Panthers committed to the offensive, Over 40% were immobilized by drivetrain issues before sustaining any combat damage. Recovery assets were overwhelmed by the volume of breakdowns. Disabled vehicles accumulated faster than recovery teams could retrieve them, blocking roads and disrupting unit cohesion. Combat losses were expected and planned for. But mechanical failures created different problems that planners hadn't anticipated. Vehicles broke down during approach marches before reaching engagement areas, blocking roads and disrupting movement schedules. They failed during tactical movements before engaging the enemy, leaving gaps in attack formations. They became immobilized in vulnerable positions where they could neither fight effectively nor withdraw safely. Soviet forces reported capturing numerous Panthers abandoned intact with technical failures rather than combat damage. German units reported Panthers that required extensive workshop time after brief operational periods measured in hours rather than the days or weeks anticipated. The mechanical attrition rate exceeded combat loss rates in the opening days, fundamentally altering the operational calculus. Intelligence summaries reaching Berlin concurrent with operational reports created uncomfortable context. The Hillersleben test data showing Panther transmission unreliability was not laboratory anomaly or testing error. Field experience validated the testing results under actual combat conditions with real consequences for operational planning. A unit readiness summary from Army Group South reported Panthers at 37% operational availability by July 20th. Tigers achieved 28%. Standard German practice considered 50% acceptable for sustained operations, though this was already pessimistic compared to Allied standards. The new vehicles failed to meet even that reduced threshold, making formations combat ineffective despite their theoretical firepower advantages. The correlation between laboratory test results and field performance was undeniable to objective observers. Reliability became the fundamental constraint on operational mass. German forces could not maintain sufficient operational strength to achieve tactical objectives because their most sophisticated vehicles spent more time broken than functional. August 1943. Detroit, Michigan. Assembly lines at the Detroit Arsenal tank plant operated in 3 shifts, producing M4A1 Sherman tanks with welded hulls. A completed hull moved along rails to powertrain installation station. Torque wrenches clicked in precise sequence as mechanics bolted the transmission assembly to the engine according to documented procedures. The production process had been refined over 18 months of continuous operation and improvement. What initially took days now required hours. The Continental R975 radial engine and transmission arrived as a complete powerpack, assembled and tested at a separate facility. Hoisting equipment lifted the assembly into the hull through the top access opening. Mechanics secured mounting bolts to specified torque values, connected drive shafts using standardized couplings, attached cooling lines with quick disconnect fittings, linked electrical systems through color-coded connectors. Standard procedure repeated thousands of times with remarkable consistency. Ordnance Department administrators monitored production schedules, showing monthly output approaching 1,000 units from this single facility. Quality control inspectors sampled vehicles according to statistical protocols developed by American industry. Training pipelines graduated mechanics, who learned their trade maintaining civilian vehicles before receiving military-specific instruction, bringing practical experience to military applications. The same automotive engineering principles that powered America's civilian economy now armed its military forces. Designers applied lessons from decades of civilian car production. Standardize components across vehicle types. Minimize custom fitting requirements. Design for disassembly and reassembly. Provide accessible maintenance points. Create modular systems that mechanics can service with standard tools available anywhere. Each Sherman carried spare parts selected based on failure rate data collected from field operations. Track blocks wore predictably under specific conditions and were stocked accordingly. Filters required regular replacement at documented intervals and were included in standard loads. The system assumed things would break through normal operation and planned for rapid repair, rather than attempting to build perfect machines that never failed. German intelligence estimates consistently and significantly undercounted American tank production, creating dangerous misperceptions. Reports reaching Berlin suggested monthly output of perhaps 300 units, already concerning but manageable. The actual figure exceeded 3,000 during peak production months. This intelligence failure of massive proportions masked the true scale of American industrial capacity and the material advantage it provided. August 12, 1943. Kummersdorf Technical Documentation Office. A clerk typed summary paragraphs for the final Sherman evaluation report using standard format. Distribution list included Armaments Ministry sections, Army Ordnance Headquarters, Panzer Development Offices, and Senior Command Elements. The report's technical section documented transmission endurance test results with scientific precision. The American gearbox completed 2,300 kilometers without major component replacement, requiring only scheduled maintenance. Panther transmissions required multiple complete replacements within 1,000 kilometers. Tiger final drives showed critical distress between 500 and 800 kilometers, requiring immediate workshop intervention. Metallurgical analysis revealed American use of high-quality alloy steels with consistent heat treatment throughout all samples examined. Machining tolerances matched or exceeded German standards in most measurements. Surface finishes were uniform across production batches, indicating process control. Part interchangeability was verified through measurements of components extracted from different production batches and assembly dates. The report's conclusion section contained language rarely used in German technical evaluations of enemy equipment, representing significant professional acknowledgement. The American transmission demonstrates superior endurance and practical design philosophy, derived from automobile industry methods. German final drives require systematic standardization of components and substantial improvement of manufacturing tolerances to achieve comparable service life under field conditions. This represented professional admission that enemy engineering had achieved results German industry could not currently replicate, despite Germany's reputation for engineering excellence. The recommendation to rationalize components and standardize manufacturing directly contradicted ongoing German tank development programs, emphasizing increasingly complex and sophisticated designs. The Panther had been rushed into production to counter Soviet T-34 tanks without adequate testing. Its transmission was new, untested in extended service, developed under time pressure. The Tiger, while formidable in firepower and protection, used components stressed beyond their design limits by the vehicle's massive 55-ton weight. Both represented German engineering priorities: powerful weapons, heavy armor, sophisticated technology, tactical superiority. Neither prioritized the unglamorous operational requirement that simply keeping tanks running mattered more than any tactical capability in sustained operations. A Tiger that broke down before reaching the battlefield contributed nothing despite its fearsome reputation. A Panther that required specialist repairs remained deadlined in workshops while the enemy advanced unopposed. The Sherman represented fundamentally different priorities that reflected different strategic thinking: adequate armor rather than maximum protection, sufficient firepower rather than overwhelming guns, reliable operation rather than technical sophistication, maintainability rather than complexity. These choices created a vehicle that kept moving when ordered, fought effectively when engaged, and returned to service quickly when damaged or worn. If you're finding value in this documented evidence of how engineering philosophy shaped warfare's outcome, consider subscribing to explore more stories where industrial reality defeated tactical theory. The intersection of design choices and battlefield results reveals lessons that transcend any single campaign. late 1943 through mid-1944. Italy and Northwest Europe, U.S. Armored unit maintenance bays demonstrated the practical advantages of American engineering philosophy under actual combat conditions. A Sherman with engine trouble rolled into a maintenance area at a forward position. Mechanics disconnected cooling lines, drive shafts, electrical connections using standard procedures. Hoisting equipment lifted the power pack out through the top hull access in one complete assembly. A replacement power pack was lowered into position from unit stocks, secured with standard hardware, connected through color-coded systems. The tank returned to service the next day, often within hours if urgency demanded. German panzer units reported chronic parts shortages that had become critical. Transmissions couldn't be replaced because replacement units didn't exist in supply channels. Track blocks were in short supply despite being wear items. Specialized components required factory production with long lead times. Mechanics improvised repairs using whatever materials were available that briefly restored function but couldn't address underlying mechanical failures. Vehicles limped along until catastrophic failure occurred. American divisions carried parts to replace approximately 10% of major components in forward stocks distributed through the supply chain. Complete engines were stockpiled at multiple echelons. Transmissions were treated as field replaceable modules, not precision assemblies requiring specialists. Standardized parts fit multiple vehicle variants, simplifying inventory. Training emphasized rapid component exchange rather than detailed diagnosis and repair procedures that required expertise. German doctrine assumed tanks would return to rear area workshops for major repairs performed by specialists. Specialized repair trains carried workshop facilities forward to reduce transportation distances. But Allied air superiority made rail movement increasingly dangerous and ultimately impossible in many sectors. Workshop locations were identified and bombed systematically. The fundamental assumption that sophisticated repairs could be performed anywhere near the front collapsed under operational reality. Readiness figures from unit reports told the quantitative story with brutal clarity. U.S. armored divisions maintained operational rates above 80% even during intense combat operations lasting weeks. German panzer units struggled to keep half their authorized strength functional during sustained fighting, often falling to 30% or below. The disparity wasn't marginal or explainable through temporary circumstances. It was fundamental and structural, reflecting different engineering philosophies and industrial capabilities. Time standards for maintenance operations illustrated the practical difference in concrete terms. American mechanics replaced a complete Sherman engine in 8 hours using prescribed procedures, standard equipment, and moderate skill levels. German mechanics required 3 days minimum and specialist tools for comparable work on a Panther powerpack. The American system was consciously designed for speed and simplicity. The German system assumed careful craftsmanship would somehow occur under combat conditions. Archive notes recorded a German engineer's assessment captured in post-war document reviews. American tanks are not elegant solutions. They lack the sophisticated engineering that characterizes German designs. But they are maintainable by ordinary soldiers, with basic training using standard tools available at unit level. This represents engineering philosophy fundamentally different from German practice and arguably more appropriate for modern warfare's operational demands. June 1943. Hillersleben Proving Ground. An endurance demonstration was arranged for senior observers, including civilian leadership. Albert Speer attended, along with Army Ordnance representatives and Panzer development officers. The stated purpose was assessing the captured Sherman's capabilities through direct observation rather than written reports. Test drivers ran a 100-kilometer circuit under observation by senior personnel. Stopwatches recorded lap times against benchmarks. Temperature sensors monitored gearbox operation continuously. Observers noted steering response, brake performance, acceleration characteristics, anything indicating stress or deficiency. The Sherman completed the run without fault or hesitation. Gearbox temperatures remained within normal operating ranges throughout. No unusual noises, no hesitation in gear changes, no steering difficulties, no visible smoke or leaks. The demonstration was unremarkable precisely because nothing remarkable occurred. The vehicle simply worked exactly as designed, performing its function without drama or crisis. A Panther ran the same circuit immediately afterward for direct comparison under identical conditions. It required workshop attention between runs when initial inspection revealed developing problems. Transmission oil had overheated beyond safe operating temperature. Several components needed adjustment before the vehicle could operate safely for another demonstration run. The contrast was obvious to everyone present. Speer's confidential note, discovered decades later in post-war document reviews, stated with unusual candor, "Our designs achieve battlefield dominance in brief engagements through superior firepower and armor protection. However, their mechanical endurance remains fundamentally unfit for sustained operations." The Panther possesses undeniable advantages in direct combat. However, the American vehicle maintains operational readiness at rates our current designs cannot match under field conditions. This observation, at the highest levels of German armaments production, meant leadership understood the fundamental problem, yet design priorities didn't change meaningfully. The Panther continued production with known reliability issues that couldn't be resolved without complete redesign. The Tiger II was developed and deployed, despite its transmission being stressed beyond safe operating limits. Emphasis remained on tactical battlefield capability rather than operational sustainability across campaigns. The political environment didn't permit publicly acknowledging that simpler, more reliable designs might serve strategic needs better than sophisticated, complex ones. German propaganda emphasized technological superiority as evidence of Aryan genius and cultural superiority, admitting that American automotive engineering, informed by decades of civilian production, produced more militarily effective tanks, contradicted fundamental Nazi narratives. The observation remained internal to technical circles. Propaganda continued, emphasizing German tank superiority through selective examples and favorable comparisons. Meanwhile, professionals quietly documented mounting evidence that tactical excellence couldn't overcome chronic mechanical unreliability in sustained operations. January 19, 1945. Berlin. A Panzer Commission meeting convened to address growing readiness problems that could no longer be ignored or explained away. A tabular report was read aloud, documenting defective drivetrain components by vehicle type across all theaters. The numbers were stark and irrefutable. 500 Panzer IV final drives reported defective and awaiting replacement parts that didn't exist in sufficient quantities. 370 Panther drives showing failures requiring workshop-level repair with specialist expertise. 100 Tiger transmission assemblies completely deadlined for major component issues requiring factory intervention. These were not combat losses from enemy action that could be celebrated as honorable casualties of war. These were mechanical failures preventing otherwise intact vehicles from operating. The tanks physically existed. Crews were available and trained. Fuel, though increasingly scarce, could theoretically be allocated. But the vehicles couldn't move because drivetrain components had failed through normal operational stress. Commission members reviewed supporting documentation that explained how the situation had developed. The pattern was clear to anyone willing to see it objectively. German tank designs consistently stress components beyond sustainable operational limits to achieve maximum performance. Final drives were undersized for vehicle weight to save space and reduce armor requirements. Transmissions lacked adequate cooling to minimize complexity. Manufacturing quality had progressively degraded as Allied bombing disrupted production and forced labor gradually replaced skilled German workers with varying results. Workshop capacity couldn't possibly meet overwhelming demand for complex repairs. Replacement parts were critically scarce because production prioritized new vehicles over spare components. Many vehicles sat immobilized for months, awaiting components that might never arrive. Operational readiness percentages for heavy armor formations fell to levels making them combat ineffective, regardless of tactical situation or crew quality. The statistical tallies reflected systemic failure across the entire armored force structure. This wasn't isolated bad luck in specific units or improper operation by incompetent crews. This was predictable consequence of fundamental design choices that prioritized maximum battlefield capability over mechanical sustainability in extended operations. Complex, powerful vehicles that spent more time broken than functional provided no practical military advantage. The contrast with American practice was implicit throughout the discussion, though not explicitly stated in formal minutes. Allied forces maintained high operational readiness through radically different design philosophy and industrial capacity to support sustained operations. German forces watched their effective strength erode through mechanical attrition they couldn't reverse through any feasible measures. The meeting concluded with acknowledgement of the problem's severity, but no realistic solutions that could be implemented. Simplifying designs would reduce production of vehicles already insufficient in numbers to meet tactical requirements. Maintaining complex designs meant accepting chronically low readiness that made formations combat ineffective. Either choice led to the same strategic outcome. Germany lacked sufficient industrial capacity to field armored forces that could compete simultaneously with Allied numbers and Allied sustainability. March and April 1945, Central Germany. Retreating German columns left heavy tanks abandoned at crossroads and field positions across the shrinking Reich. Tigers with seized final drives that couldn't be repaired. Panthers with failed transmissions awaiting parts that would never arrive. The vehicles appeared superficially intact. Armor unperforated by enemy fire. Guns still operational if they could be crewed, but they couldn't move under their own power. Demolition charges were reserved for bridges and critical infrastructure that might slow Allied advances. Individual tanks were simply abandoned when they broke down, and recovery was tactically or physically impossible. Crews removed personal equipment, extracted breech blocks from guns if time permitted, and withdrew on foot or in remaining operational vehicles. American technical intelligence teams systematically cataloging abandoned equipment noted the consistent pattern. A significant percentage of German heavy armor losses weren't from direct enemy fire or tactical defeats. They were mechanical casualties, casualties of design choices and industrial limitations, transmissions that overheated and seized solid, final drives that fractured under sustained operational stress, engines that failed without adequate maintenance support in the field. German workshop personnel forced to withdraw under pressure documented their frustrating experiences. They had worked continuously repairing vehicles only to see them break down again after brief operational periods. The Tiger and Panther designs demanded constant expert attention that field conditions couldn't provide. Components required frequent adjustment by specialists who often weren't available. Complex systems needed specialist knowledge that couldn't be taught quickly to replacement personnel. Under combat conditions with limited resources and constant movement, maintaining adequate readiness proved impossible despite heroic efforts. Allied repair echelons kept pace with advancing forces through different organizational approaches. Mobile workshops performed complete engine and transmission replacements at forward positions. Replacement parts were systematically trucked forward from deep supply depots. American and British tanks that were damaged or mechanically worn were efficiently repaired and returned to combat service, maintaining divisional strength even during intense combat operations lasting weeks. The operational verdict preceded the formal armistice by weeks. Readiness, not design novelty or tactical sophistication, determined which forces could occupy ground and hold territory. German tanks that couldn't move contributed nothing militarily regardless of how powerful their guns or how thick their armor. Allied tanks that kept running reliably, even if individually tactically inferior, achieved operational objectives through sheer availability and presence. 1946 and 1947. Occupied Germany. Allied technical commissions systematically examined, captured Kummersdorf and Hillersleben files and archives. They compiled comprehensive comparative studies of German and Allied tank development programs. The extensive documentation provided German perspective on their own equipment's shortcomings as understood by their own engineers. The detailed test reports validated what Allied field experience had consistently shown across multiple theaters. American automotive engineering principles produced substantially superior operational availability under actual combat conditions. German precision manufacturing created technically sophisticated vehicles that demanded constant expert attention impossible to provide in field conditions. One commission report noted with professional interest, German test data comprehensively confirms American maintenance advantages stem from fundamental design choices, consciously prioritizing field serviceability and component durability. German engineering practice emphasized maximum performance characteristics, achievable only through complex mechanical systems, requiring extensive specialist support that proved unavailable under field operational conditions. Members of former Prüf 6 testing staff provided valuable procedural context during extensive debriefings. They explained standardized testing protocols and documentation procedures. They discussed how analytical data was processed, interpreted, and reported through command channels. They acknowledged candidly that German leadership often systematically dismissed unfavorable assessments of German equipment performance, while accepting optimistic projections and claims largely uncritically. The endurance logs, comprehensive parts interchange assessments, and detailed maintenance man-hour comparisons documented with scientific precision what ultimately determined campaign outcomes. Tanks that run reliably when operationally needed win campaigns through sustained presence. Tanks that break down frequently lose campaigns, regardless of their theoretical tactical capabilities or crew skill. Post-war reviews conducted with access to complete records reaffirmed fundamental conclusions. American automotive engineering methodology and comprehensively standardized logistics systems produced demonstrably superior operational availability under sustained combat conditions. This represented strategic advantage substantially more decisive than any tactical innovation or technological breakthrough. These findings directly informed future military doctrine development, emphasizing practical maintainability, functional modularity, and training depth across all equipment categories. The archival conclusion, based on comprehensive evidence, matched observed battlefield reality perfectly. Robust, maintainable systems consistently outperform exquisite but mechanically fragile ones, when sustained operations over extended periods determine ultimate victory. 1945 through 1969. From occupation zones to published memoirs, the technical lessons of tank reliability slowly entered broader public understanding beyond specialist circles. Albert Speer's memoir, Inside the Third Reich, published in 1969, reflected candidly on wartime industrial choices and technological constraints. Public myth persistently celebrated supposedly invincible German heavy armor as symbols of martial excellence. Tigers and Panthers dominated popular imagination as iconic symbols of technical superiority and German engineering prowess. The detailed historical record based on actual operational data told a fundamentally different story. Production totals revealed the true scope of American industrial advantage: 49,324 Shermans manufactured across multiple facilities, roughly 6,000 Panthers produced under increasingly difficult conditions, 1,347 Tigers completed before production ceased. Against these stark numbers, German technical sophistication became historical footnote rather than decisive strategic factor. Average operational readiness statistics from unit reports emphasize the crucial operational point. American armored divisions consistently maintained above 80% operational strength throughout sustained campaigns. German panzer divisions often fell below 50% during sustained operations, sometimes dropping to 30% or lower. Recovery timelines showed similar disparities. Shermans were routinely repaired and returned to combat service in hours or at most days. Panthers and Tigers required weeks when complex components failed, often remaining deadlined indefinitely for lack of spare parts. Speer's candid admission, published decades after the war when he could speak freely, captured the fundamental philosophical difference. The Americans understood the military machine as an integrated mechanical system requiring continuous support. We understood it primarily as a tactical weapon, and assumed somehow the support would materialize. This philosophical divide shaped everything about how tanks were designed, produced, and supported operationally. American engineers consciously designed tanks as complex mechanical systems, inevitably requiring regular maintenance and planned comprehensive support accordingly. German engineers designed tanks primarily as tactical weapons, optimized for battlefield performance, and assumed maintenance would somehow occur through traditional military craftsmanship. The first approach created genuine operational sustainability. The second approach created persistent readiness crisis that worsened progressively. Strategic success in armored warfare followed directly from systematic engineering approach. Standard parts manufactured in large quantities allowed rapid replacement anywhere in the supply chain. Trained mechanics performed complex field repairs without specialist intervention using documented procedures. Repair cycles were deliberately designed, measuring in hours rather than days or weeks. These seemingly mundane advantages accumulated across thousands of individual vehicles and millions of operational hours to create overwhelming superiority in sustained combat operations. The war's final statistical ledger decisively favored the tank that moved reliably when operationally ordered. Mechanical reliability, thoroughly documented in controlled tests and repeatedly proven in extended campaigns, emerged as the truly decisive technology. Not maximum firepower, not heaviest armor, not tactical sophistication or crew skill. The fundamental ability to keep moving, keep fighting, keep running reliably until operational objectives were decisively secured. The Sherman tank conclusively proved that adequate firepower, adequate protection, and superior mechanical reliability defeated superior firepower, superior protection, and inadequate reliability in sustained operations. This crucial lesson, written clearly in German test reports and verified through 4 years of intensive combat across multiple theaters, established fundamental principles that would guide armored vehicle design and doctrine for decades afterward. If you value rigorously researched documentary history, grounded in verified engineering records and objective operational analysis, consider exploring additional content, examining how industrial decisions and fundamental design philosophy shaped actual military outcomes. The critical intersection of technology, industrial production capacity, and operational reality determined campaign victories far more surely than tactical battlefield maneuvers or individual combat engagements.